So, in this question, we're thinking about the number of sick days that a company's employees are actually taking. And what we are supposing is that in the past year, there was a mean of 5.4 sick days. And then some policy changes, and we take a sample of 80 employees, and these employees average 4.5 sick days. And there's a sample standard deviation of 2.7. So, what we want to test is the mean actually reducing, right? So we want to test the null hypothesis that the new policy has a mean which is greater than or equal to 5.4, which was the old mean. And that's because the alternative here is that we're going to have this one-sided hypothesis test, where the alternative is that we're actually reducing the number of sick days, right? The other pieces of information that we're given here is that n is equal to 80, and that the computed x bar is going to be equal to 4.5. And finally, what we're told is that the sample standard deviation is going to be 2.7, right? And so we have to think about a couple of things, right? So the first, we have our hypotheses actually laid out here for us, right? But if we hadn't been told to specifically test the hypothesis, maybe we would have been asked to test the hypothesis that the number of sick days has reduced with this new policy, right? Which would set us up into the same place. In this question, we're not actually given an alpha value, right? So we have to decide what is a threshold that seems reasonable for us to do here. Whether you want to pick alpha equals 5%, 1%, something smaller than that is going to be a little bit up to you. In this case, of course, we don't know how big of stakes are there for this actually being incorrect, right? And so, depending on sort of how much the company cares about getting this right, you might need a smaller or a larger alpha. We'll take alpha to be 0.05 in this case because it's a familiar value for us. But what I really want to actually focus on is once we work out that p-value, let's see sort of what is the thresholds at which we would be making different decisions, right? Is it going to be a really low p-value where sort of doesn't matter what significance threshold we pick, or is it going to be a high value p-value where we're going to actually have to think a little bit more about this, right? The other thing to note here is that we're in the situation where we have a fairly large sample size, right? So we have n equals 80. And so what that means is that we can actually use the central limit theorem as the approximation. And so what we'll do is we will think about the test statistic, x bar minus mu naught. In this case, we'll divide by s over the square root of n, right? And we're going to say that this is going to be approximately normally distributed without knowing even what the underlying distribution is because we have this larger sample size, right? If we were only dealing with, say, 15 individuals in the sample, then we're going to have a harder time using this approximation. And then we would want to know, is the underlying distribution normal so that we could actually still run this hypothesis test, right? But with this sort of setup in mind, right, what we can do is we can actually work out what is the test statistic that we've computed here, right? So x bar is going to be equal to 4.5, right? That's the number of 6 days that we've observed on average within our 80 individuals. We're going to take off the 5.4, which was the assumed null value, right? And then we divide by our 2.7, which is our sample standard deviation, over the square root of n, which in this case is going to be 80, right? And so then we can actually sort of work out trying to simplify this fraction down a little bit. And if you just plug this into, say, your calculator, you should get negative 2.981, right? And so we'll just use that as sort of our approximate value. It's going to be good enough for the situation that we're in here. And now, again, once you actually have your test statistic computed, it's worth plotting what it is that we're actually thinking about in the scenario here, right? So if the null hypothesis is true, then the test statistic that we just computed is going to be approximately normally distributed, right? So let's think about what that actually looks like, right? So we have our graph here. As always with these things, your graph doesn't actually have to look that good. Mine very rarely does, right? But it's just going to give us this sense. And then what we're saying is that we're observing this value that's around -3 over here, right? So -2.981. And the question for us is, what are the values that are more extreme than what we've actually observed here? And again, we should be thinking about the fact that we're using a one-sided hypothesis test here, right? And so only values that are going to be more negative are going to be considering sort of more extreme for us, right? And so the p-value is going to be this area that we're shading in here, right? It's going to be the probability that you're less than or equal to -2.981. When we're doing this one-sided hypothesis test, the nice part for us is that this is exactly the definition of the CDF, right? And so what we can say is that in this case, the p-value is going to exactly equal phi of -2.981, where remember phi is going to be the CDF of the standard normal distribution. Now, as always with these normal values, we're not going to expect to compute them by hand. And so instead, we would turn to software or tables of values or similar. And if you do that in this case, what you find is that this is going to be approximately 0.0014, say 0.0014, right? And so ultimately, if we're thinking about drawing a conclusion here, it's not going to matter whether we picked 1% or 5% or 10%. All of these values are going to be significant, right? If you had picked anything that's above 0.0014, you're going to determine that there's statistical significance here. And so we're going to reject the null hypothesis, and we're going to conclude that, yes, in fact, this policy has actually reduced the number of sick days that employees are going to be taking on average, right? And again, we'll point out that if this had instead been the null hypothesis was that the policy produces the exact same number of sick days, right, versus the alternative of inequality here, then in this case, right, if we just mark this in blue, we'd also want to consider up here at the positive 2.981, right? So then we'd add on these two areas. P-value is going to be double that, but even at double the p-value that we're looking at here, we're still thinking that this is going to be statistically significant at most significance levels that we're going to care about, right? And so here you can conclude that this policy actually does make a difference. It seems like under the new policy, there are really going to be fewer sick days. Now, once you have that conclusion, you'd want to turn to practical significance, right? Our estimated difference between these two is less than one, or just over, right around 1 sick day per person, right? And so does reducing by right around 1 sick day per person make a big difference? It might not. It's going to depend on the situation there. Our stats methods can't tell us whether that matters or not. You'll have to turn to the subject matter expertise to decide that.